put a flash memory inside. Then we can have external, along with that you can put external 12-bit ADC 7109. Okay. Don't use 7106 or 07. Use 7109. Okay. And use that. Okay. Or if you don't want to use this, you can use ISAC. ISAC is stands for Intelligent Sensor Actuator Controller, made by Android devices. It has got a built-in 12-bit ADC and 12-bit TAC. You can use this if you get it. They get from Android devices, you get a board and the controller together on a single chip. You can use that for the or you can use a Siemens microcontroller ATC 535 or ATC 552, which has got a 10-bit ADC and a 2-bit reference change. So effectively you get a 12-bit ADC. Now what should be the number of bits available in the ADC? Should I use 8-bit or a 12-bit? That's the question you must ask. Looking at what is the level of DC signal and what is the level of AC signal. If the DC is very large compared to the AC signal, you must go for a 12-bit ADC. Okay? If there was no DC and you were only AC, I would have done with 8-bit ADC also. Now these are high-speed AD converters, around 60 microseconds or less than that. 60 microseconds you can convert one analog quantity to a digital number. In 7109, that's going to be a problem. They are slow AD converters. So for a slow sampling, when the data is number of data points in a kernel are less, then you can afford to go for the 7109 configuration because the conversion time is large. If you have got high-speed ADC required, because you want more data points in a smallest possible interval of time, then your option is, the best option is ISAC. Okay? Otherwise you can go with this. There are a lot of software manipulation has been done here because they are only 10-bit ADC and you have to resolve the convert at 10 to 12 by dividing the reference signal. So I would give an option for this for implementing processing. Of course, I have done it with this shape or not I have to Plus, this supports what is known as the DMA mode, direct memory access. So, normally what happens, you want to write something into the memory from an ADC converter, you have to get the data from the ADC using the port lines into the accumulator, and from accumulator you have to go to write to the memory location. If you want to avoid that, then you can use the direct memory access because the data comes from ADC and goes straight into the memory. So, you don't have CPU intervention for doing that job. So, the faster implementation can be done using ADC 12. Is this point clear? So the choice will depend on what is the conversion time of ADC vis-a-vis the number of sample points that you want to have. Then whether it is a DMA mode supported or not. And thirdly, whether the 12-bit is intrinsic or extrinsic. Extrinsic means they have to divide that, convert that 10 to 12 by software. So there are more overheads. Right. So looking at this, on the top you can see, let me scroll it down. In a nutshell, this is a good paper available from HP. It will be got on the approximately. It's there in the folder. You can have a look at it. It's a 12-page paper. You can read it whenever you have time. But today I'm just going to explain to you. This is on the diagonal arrays, anti-parallel. Get my point? So when the current flows, see there are two directions for the current. ILE. When ILE is going inside the triangle, it is called sink. And when it is going outside the triangle, it's called source. So when the sources come, the red is going to be on, and when it sinks, the equivalent is going to be on. Therefore, they are anti-parallel to each other. Right? So that's you can say a buffer through which you are controlling the direction of the. In fact, it's not really a buffer. It's called Holland current pump, where the direction of the current can be controlled and the magnitude of the current also can be controlled. That's a separate topic by itself. You can read Holland current pump. Pump means a circuit which can source and sink current, which can be digitally set. So you have a numerical value that is 0, 0 to FF, which will decide what should be the amplitude of the current, and the direction of the current is decided by the 9th bit, whether you want to flow out or flow in. So by doing this, you can see there are three states. You can tell so then once the red is on, then the infrared is on, and then both are off. When the red is on, infrared is not there. You get my point? So it has to be either red or infrared or both off, so it becomes ambient. Now, there is a common detector. Only one detector is there, photodetector. In transducers, you have sensors and actuators. Now, this is the sensor, which takes the light in and generates a current out. And this is a transconductance amplifier, which will convert that current into voltage signal. Simple. In the feedback path, you put a resistance. So when the current flows through this, you get the output voltage proportional to the flow of current. Now, what will be the direction of the current? Is this the correct direction? Photodiodes, the reverse current will be proportional to the amount of intensity of light falling on it, not the forward current. So the direction is not correct. Or if you take this direction, you are going to get a saturation. You are not going to operate as a photodiode. You are going to make it a power bias diode. Remember, this is something which you start working with the device will come to know. It's a reverse current which is proportional to the amount of light which falls on it. And that current is converted into voltage by this current to voltage converter. And then you have 3 sample and load circuits. So once you switch the red, then you switch the infrared, then you switch the ambient. Now what you have done here, instead of having 3 channel ADC, you are doing 2 channel ADC, and you are doing analog subtraction. See, this signal, which is common ambient, is taken from the subtracted from these 2, red and infrared, and you get only 2 outputs. So with this method, what you are saving? You are saving 1 stack of memory for storing ambient light. You are doing analog subtraction. Are you with me? Yeah. But what happens in analog subtraction when you do it, you lose the information because you are not storing that information. If you want to know how the ambient light in this room changes as a passage of time, then you must have 3 channel AD converters so that you know that if somebody puts a tube light on, the ambient is going to be different, in the night the ambient is going to be different, in the day the ambient is going to be different. So if you want to make an ambient monitoring, don't put the LED on, just put the detector on. This is ambient light, and you can do ambient light monitoring on this room. So advantage of using the analog subtraction is that you require 1 channel less, you also require 1 less stack, but you lose the information of ambient at the time. So that is subtracted at the analog signal level itself. Are you with me? What you lose by doing this method is the loss of information for post-processing. Okay. And this can be a major factor which can cause errors in the measurement. A very high ambient will give a DC level which will not allow you to see the AC. And you will get a signal as there is no drive flow because AC is very small compared to DC. Okay. The DC which comes from the tissues is different from the DC which comes from the ambient. But it's a very low frequency. I mean, unless somebody comes and turns on this light every now and then the ambient of course will be changing very fast. Otherwise, the ambient changes very, very slow. And you can put a bypass filter and remove that ambient component also from the signal. So this is what you have extracted from this data. Information corresponds to the red light, information corresponds to the infrared light. So you are getting 2 waveforms, which you can see on the graph below this. You can see this too. This is the infrared and this is the red. Now what you are doing is you are digitizing each and every point on this waveform. But remember, you are going sequentially. You are taking red, then infrared, then ambient, again red, infrared and ambient. You are not doing them concurrently. Ideally what should happen? Ideally you must have 3 individual single channel ADCs. Remember. Then you can do concurrent processing. In the sense, all these signals will look at the same time at the red, at the infrared and the ambient. So what is the advantage of that? You can increase the number of data points. So exactly 3 times of that. So you have more refined data being stored because you are not losing information. Because you are doing red sampling, you are losing the information of red and ambient, different ambient. If you are doing infrared, you are losing the red and ambient. If you are doing ambient, you are losing red and infrared. So ideally speaking, what should happen is put the red, infrared and ambient together at the same time. Right? And then have 3 individual ADCs, not 3 channel ADCs, 3 individual ADCs which will do the processing in parallel. And you will have 3 data points taken at the same time, so snapshot, like look at the 3 signals, take a snapshot once, then second, then third. So all the 3 data points are taken at the same time, not sequentially. Get my point here? So this is a second approach which is more expensive. Using a parallel 3 ADCs would cost you more hardware. And it will also cost you more in terms of memory because you are going to have larger number of data points now. Here what happens is you get 1/3 data points for red, 1/3 for infrared and 1/3 for ambient. So you are talking about 300 data points. It would be 900 data points if you do a snapshot of parallel 3 conversion. Are you understanding this difference? So if you want more data from the curve, I would recommend to go for a 3 parallel ADCs working on the 3 analog signals separately. It will cost you in terms of memory locations, it will cost you the processing time, but many times the wave shape of that is also very important feature than only the amplitude and the time. There is a lot of information you can extract from the wave shape. That is what is the bandwidth of that, what is the 3 dB points of that curve. You can count that, you can make out. You know what is 3 dB points. You have the top point, you take a 0.7 of that, and this is a 3 dB point. You can the 3 dB width, and 3 dB width can also give you information about whether the patient is sleeping or whether he is standing, in what conditions the data is taken, and that also information can be used to remove the noise component. Now this information has a lot of noise, as I told you, the radiated noise, the conducted noise, a low frequency shift because of the DC and the ambient signal. When the patient moves his hand from one place to the other, there is a DC shift which is going to take place. Then there is a cautery machine which is being operated in the hospital that generates a radiated noise which will also affect this reading. So you will make a more and more costly instrument, or rather good instrument. You are going to take care of all these noise components and remove them from the analog information that you have stored. It's very easy, right? You take a moving average and you can remove the high frequency component. You know that, that's the standard method. And from the data, if you remove the moving average, you get a high frequency component. So you can remove the noise. There are various algorithms available for removing the noise digitally as well as remove the noise at this level itself. You can also write a filter here, analog filter design, and you can remove the high frequency noise and the low frequency traits. Best is to put a band pass filter. And that band pass will have a frequency from 1 Hz to 2 Hz, or at the most from 0.9 Hz to 2.1 Hz. You get exactly the frequency between 60 to 120. Everything else will be cut off. Plus, the sampling itself generates a noise. When you are doing sampling, it generates a noise by itself. So, must do a sampling at a much higher rate. What's the Nyquist criteria? 2 times this input signal. It's not. That's only going to give you only 2 data points. The more the data points you want, the more should be the sampling frequency compared to original. If you want 1000 data points per signal, if the original frequency is say 1 Hz, the sampling frequency has to be 1 kHz. So this is something which you, unless you start writing algorithm and programs, you will not be able to appreciate those fine details, because when you reconstruct this the data on a screen on a CRO, you find the original signal is seen on a SWIGL, and you recreate a signal. The signals will not match because you have created what is known as quantization error. And to remove the quantization error, the correct method is to do parallel sampling. Are you getting my point? One thing is you are not doing, you are doing sequential sampling, that's why you are losing information. But you are saving on the memory. But if you do parallel sampling, you get all the 3 data points at the same time, but you are going to cost you in terms of memory and the processing time. But you are very close to what the real world is. But what is happening? You are also putting the radon and infrared on simultaneously. So it's going to cost you power. So you have to weigh all these things with respect to the final end result that you are interested in. Suppose I am making only a fingertip sensor, I don't have to put all this noise elimination and everything. Anyway, that's a very crude method to find out whether the person has oxygen level which is close to 97, 98 or not. It doesn't really matter whether it is 94 or whether it is 99, because he only sees that he doesn't require oxygenation. But if it's an ICU, you have to be very careful about every one point, that is whether it is 87, 86, 85, and there if you make any errors in the measurement, you have it. You can lose the patient. So the intricacy, the application, end application will decide what should be the choice of ADC, what algorithm you would like to use, and then lastly, when I said you want to create a log of the patient's information over the entire 3 or 4 days, you require a large amount of memory, either within the oximeter or you can have the external memory bank. Keep on dumping this data into the external bank, and then that's where the cost goes up. Okay, now what cosmetics can be added to this is that you can give a connectivity which is called the internet connectivity for this embedded product by putting a hardware stack, a 5-layer hardware stack onto the board. Like, for example, you get boards like this. Okay, there's a lot of area available. This is a ARM microcontroller which is sitting here. And you have a standard, you can have a alphanumeric or a graphic display, whichever you want. You can add a Bluetooth chip, you can add a Wi-Fi chip, you can add an Ethernet chip. Ethernet chip is made by BizNet. So BizNet gives you a hardware 5-layer stack. So as if you are writing to 8279, you can write to that chip, and that will take care of sending the data onto the Ethernet, the local area network. Once you have a local area network, Ethernet is not required. Are you with me? If I want a MAC address for this board, which you get by putting the visit chip, this board becomes unique.